Okay, so the announcements for today are actually a couple of questions for you guys. One of them is quiz number 4. I originally put on the syllabus as being next week, but I feel like that's pretty much going to end up being just like if we cover up through the end of lecture today, like a tiny bit of chapter 23 and then a bunch of exam review stuff. So since all our recitations are on Wednesday and Thursday, how would you guys feel about pushing it back a week to the last week of class? So hands up, keep it where it is. If you prefer to, yeah? Okay. And then, okay, sorry. So raise your hand if you want to keep the quiz where it is right now as next week. And raise your hand if you want to push it back a week. Okay, sorry. I think keep it where it is wins. So quiz number 4 next week. Okay. And then the other question I have is the exam review session. I haven't actually looked at room availability. So our final is on the early on Wednesday morning of finals week. I know like a lot of people have finals all over the place the few days before that. I was actually thinking like sometime around like late morning, early afternoon on Friday the week before on Dead Day. Raise your hand if that time would work for you. Okay. How about later in the week, like on Saturday? Okay. I don't know when though, sorry. It's totally dependent on room availability, which is a little hit or miss. So this is all like contingent on me getting in touch with the, yeah.
What about Sunday at 8?
I actually have something going on then, sorry. Okay, late afternoon, Sunday. Yeah, that would work for me. Hence, show of hands, like who all would like Sunday afternoon / evening? Okay, that seems pretty popular. Okay, later in the week we might be starting to overlap a bunch with other people's finals. I'll try to book the 2 to 4 Sunday thing again, or maybe like a little bit later. I have something starting at 5 on Sunday, but yeah, like we could go till 4-ish if that works. Okay.
Wait, what time were you on Sunday?
Maybe the same time as the other exam reviews. So does that? Okay. 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 Oh, all right. Yeah, I'll see what I can grab. So a lot of this is very up in the air still. That's okay. 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 Alrighty, so quiz number 4 is next week, and the exam review for the final sometime on Sunday, if I can swing it. We'll see what I can get set up. Okay. Any other questions about that stuff? Okay, cool. Alrighty. So hopefully you saw I've got the chapter 23 notes posted on the website. So we only have a couple chapters left in the semester, and guys, fortunately they're both reasonably short ones. So the last 2 chapters we're going to do before the final are, first of all, amines. We're going to bring together a bunch of nitrogen-containing chemistry, bits and pieces of which we've seen elsewhere, but now it's all in the one place, plus some new stuff. And then chapter 24 is actually like a little bit of an intro to biochemistry. I'm getting into carbohydrate stuff a little bit. So that is pretty different. This is the last like functional group centric chapter we're going to cover. Okay. So hopefully you are familiar with amines. Basically it's just R groups attached to nitrogen, but you have a fair bit of variability in how many R groups you can have. So nitrogen with no R groups and just a bunch of H's to fill those places is ammonia. If you replace one H with an R group, it's a primary amine. If you replace 2 of them with R groups, it's a secondary amine. 3 R groups, and it's a tertiary. All right, so that's all pretty analogous to how we saw it for carbon, like carbon with 0, 1, 2, or 3 bonds to other carbons gets described differently. 4 bonds is a little bit different because you can't put 4 R groups on a nitrogen without putting a plus charge on it too. Like nitrogen for all of these has a lone pair if it wants to stay neutral. And so squeezing a fourth R group on there means we lose the lone pair and nitrogen takes a plus charge. So this is called a quaternary, just like quaternary carbon, but it's a quaternary ammonium. So that IUM ending usually means positive charge on whatever. Okay. All right, so questions about those? All right, cool. So I guess the big difference here between nitrogen and, say, like alkyl halides or alcohols is that usually with alcohols, say we have this thing, we would describe this as a primary alcohol because it's attached to a carbon that is primary. And like secondary is attached to a secondary carbon, tertiary is attached to a tertiary carbon. So we're not really looking at the functional group itself. We're usually looking at the carbon that it's attached to. For amines, though, we're describing things in terms of what the nitrogen itself has actually got, because it actually has a lot of flexibility in terms of how many R groups it can have. So just as a heads up, like, it's not exactly the same descriptor that we would use for some other stuff, so don't get thrown off by that. Okay, questions about that? All right, cool. Okay, so like a lot of the previous chapters, we're going to spend a little while on nomenclature and then get into reactions. Okay, so nomenclature, and like always, we're going to spend a little bit of time on older common naming and then most of the time on IUPAC name. Okay, so if there's one R group, so in other words, for primary amines, name it as the alkyl plus the word amine. So like this one, a nitrogen with a single methyl group on it, is methylamine. If we have for two R groups, we're going to call it di whatever amine, or for 3R groups, triamine. So this one would be dimethylamine. And this one would be trimethylamine. Okay, so that's fairly simple, as long as all the R groups are the same. For different types of R groups, we're going to name the molecule after whatever the larger group is, with the larger group being unfortunately poorly defined because this is not really an organized system very much. So we're going to name after the larger R group with the smaller alkyl groups as substituents at the end position. Okay. So for example, this one, we're going to assume that this cyclohexyl R group takes priority. So this would be a cyclohexylamine. And it also has an ethyl group attached to the nitrogen. So N-ethyl cyclohexylamine. Okay. Okay. So we are going to see a few kind of common aromatic names that got grandfathered into IUPAC again. So this one is aniline as the parent name. So we could have other substituents on there too. So this one would be like N-ethyl aniline. Or we could have other stuff on the ring, in which case we'd have to resort to ortho, meta, para, or just use substituents locations. So like meta nitroaniline. Okay. Questions about this? Okay, cool. So IUPAC is actually real similar to common for this. The ending of the name changes a little bit differently though. Okay. So drop the E from the name and add amine. So this one, it's a pentane is the parent. So we're going to drop the E from pentane and add amine. So it's pentanamine. And because there's multiple locations that nitrogen could be, just like if it were pentanol or pentanone or whatever other functional group, we're going to have to include a descriptor there. So 2-pentamine or pentanamine. Okay, this one is pretty similar to the non-IUPAC naming. Here the parent is cyclohexane. So cyclohexanamine is the parent. And then again, we're going to have substituent locations for the nitrogen. So N-ethyl cyclohexanamine. Okay, what common doesn't cover is, just like for other functional groups that we've seen, we can have multiple copies of that functional group and still come up with a name. So this one, parent chain is 1, 2, 3, 4, 5 carbons. It's pentane based. So what we've done in the past, if we had 2 copies of an alcohol, for example, we would keep the E and add diol, triol, tetraol. Same thing here, we're going to keep the E and add diamine. So pentane, diamine. So this would be, again, we got to give substituent locations, so 1,5-pentane, diamine. Okay, so same basic pattern that we've seen pretty much throughout this entire semester for naming functional groups. Okay, and then finally, if we have substituents coming off of both of the amines in something that's got a diamine or more, then we're going to have to give different end locations for those things. Let me move over here for this one. Okay, so here you have to figure out, I guess, when you number the parent chain. So the nitrogen at the lowest number on the parent chain is just called N as a location. Then the next one is N prime. Then N double prime. Putting these in quotes was a bad idea if I'm going to do so many primes. All right, so N prime, N double prime, and so on for however many nitrogens you have. Okay, so for example, this thing, we've got propane as the parent chain. It's propane diamine. The only difference between the ends is one has a methyl, one has an ethyl. Ethyl comes first alphabetically, so we're going to number this thing as 1, 2, 3. So this would be location N. So N ethyl, N prime methyl, propane diamine. Oh, 1, 3 propane diamine. Okay. So questions about that one? Oh yeah. So I don't actually know where they rank compared to the other ones. I'm sure that one appendix in the back of Loudon will probably say, but I didn't actually check before I was putting this together. So yep. Sorry. So the same kind of rules that we've used for numbering the parent in the past, where if everything else is equal and the molecule is symmetric other than that, then it's just whichever gets cited first alphabetically. So ethyl ends up winning over methyl. So, okay, cool. Okay. All right, so there are a few other cyclic ones that have nitrogen as part of the actual ring instead of coming off of an aromatic ring. So N heterocycles is how we might describe those rings where they have heteroatoms, which are specifically nitrogens in them. Okay. I think we actually saw, I don't remember if I included it in the notes, but if you guys remember on the Grubbs catalyst, there's one ligand on there that's NHC, that's N-heterocyclic carbene. So that's kind of what this is, just some kind of ring with a nitrogen in it. But there's a few names here that I don't expect you to memorize, but you may see popping up now and then. Okay, so Piperidine is basically cyclohexane with a nitrogen. Morpholine is that with another oxygen. Pyrrolidine, 5-membered ring. Aziridine is basically epoxide, but with N instead of O. And then finally, a couple that we actually have seen explicitly before, one of them a bunch. So this one, an aromatic ring with a nitrogen in it, is what? Pyridine, yeah. And the 5-membered equivalent is pyrrole. Okay, so don't have to memorize those, but that's what they are if you see them. Okay, any questions about that? Okay, cool. All right, so before we get into actual reactivity, there's actually one other kind of interesting physical property that we're going to look at here, or behavioral thing, I guess, and that is structure of amines. So like electronic structure. Okay, so I actually talked about this real briefly a while back, but now we're going to look at it some more. So nitrogen with, I guess I should say more specifically, amines have an sp3 hybridized nitrogen. So it's tetrahedral. So if we draw it as like R3, R2, R1, those three groups together with the lone pair are making a tetrahedral pyramid. But like we saw a little while ago, I think it was a long time ago, like in the alkynes chapter, when we looked at forming alkenes via dissolving metal reduction, when one of the groups in this tetrahedron is a lone pair, it doesn't actually stay fixed. It can actually invert through the nitrogen. So we can sort of do this thing where, real briefly, nitrogen can go trigonal planar. As the lone pair sort of evens out onto either side of the nitrogen. So we go sp3 briefly sp2, and then when it pops back out into sp3 again, it can actually come out on either side, which can invert the stereochemistry at nitrogen. So pretty much, even though nitrogen's tetrahedral with 4 different things on it, it's not considered an asymmetric atom of any kind. So stereochem can invert easily there. So it's not an asymmetric atom. Okay. However, if we change the 4th group on nitrogen for another R group, like if we make it a quaternary ammonium, then it's locked because it can't do this thing anymore. So this thing doesn't invert. So this actually is an asymmetric atom on the nitrogen. Okay. So any questions about that? Okay, cool. Alrighty, so with that done, we're going to get straight into the reactions now. Oh, yeah.
So are carbanions considered chiral if they have 3 different groups on them?
Generally, no. I'm not sure how fast the inversion there is compared to nitrogen. Like, there's probably some physical organic stuff going on that I don't know about, but I bet they invert fast enough that, yeah, you wouldn't consider them chiral either. Yeah. Okay. Alrighty, so the first kind of group of stuff that we're going to look at in this chapter is alkylation. And we've seen a bunch of stuff that fits into this category, but we're going to look at why some of it is not as good an idea as it looks at first glance. So the first thing that comes to mind is just SN2 on an alkyl halide. We know that we can do that pretty easily. So like if we want to get, say, this nitrogen here, if we want to stick a methyl group on it, why don't we just do this, where we bring in like a really good SN2 capable alkyl halide, go do SN2, and temporarily I'll have a plus charge on there, and then whatever else, maybe like another nitrogen or whatever's handy. Can come pull the H off, and there we are. We stuck a methyl group on there. Looks pretty easy, right? Unfortunately, it's too easy because this thing is not going to stop at just one if you have multiple equivalents of this around. As soon as you regenerate that lone pair by deprotonating it and getting back to neutral, it's just going to keep going. That gets you to there. Deprotonate again with whatever nitrogen is around. Get the lone pair back, and assuming that you still have methyl iodide around, it's just going to keep going. So eventually, you end up at, I'll skip showing the third one. But you get to where you have 3 methyl groups on there, and even then it still doesn't stop. It still has a lone pair. It's still going to do SN2. Until finally you remove its ability to do this by not having the option to deprotonate anymore. So pretty much if there's enough methyl iodide around, it's just going to over-alkylate. See the quaternary ammonium. If you try to throttle this back by having fewer equivalents around, it's not going to go as well as you might hope, just because sterics are not as big a deal on this. I think, at least if you're doing for methyl iodide, like you can still do SN2 on methyl iodide even if your sterics are not great. And so trying to slow this down just ends up giving you a mixture of things where some end up with no alkyl groups and some end up with multiple alkyl groups. Okay, so this is called quaternization. Or it's also called exhaustive methylation. If your R group is methyl like it is here, which it frequently is because that's the easiest one to do SN2 on. Okay. This also happens if you try to use nitrogen to do other nucleophilic attacks that we've seen in the past. I don't think I ever explicitly showed nitrogen going after an epoxide, but that is actually totally a thing you can do with it. So nitrogen here can go attack an epoxide, pop that open. And get this briefly, which can immediately go do proton transfer. And add one of these CH2CH2OH groups. But then the nitrogen doesn't really get slowed down by doing this. Once it loses this proton, it's good to go again. So you just do this repeatedly until you end up at nitrogen with 3 epoxide-based pieces on it. This one you may or may not add a 4th. You've got a little bit more of a concern over pKa values because you're creating an O- by doing this. So it kind of depends on what pH you're doing it at, I think. Okay, one other thing that we also didn't explicitly look at this particular setup, but we saw something really similar at the end of the last chapter, is nitrogen is one of the nucleophiles that prefers conjugate attack. So if you have and I don't know why they chose this reaction specifically to include in the book as an example, but it might come down to pKa's actually, but if you have nitrogen here, it's going to do conjugate attack onto this thing that's basically a conjugated carbonyl, only it's a different type of acid derivative to having an actual carbonyl. But it can do something similar where double bond there, and then this could do proton transfer. Actually, no, that is not how that happens. Sorry, I didn't include the mechanism in the notes, and now I'm remembering. Okay, so instead this is going to do enolate type chemistry where this comes down, and then this picks up the proton off of here. So you end up with this kind of cyanide-ended chain here attached to the nitrogen. And then you can do that multiple times too. Okay. Okay. So for all of these, like, you don't have to know the exact reagents that we're using, but just be aware that all of the types of nucleophilic attack that we've studied with just a regular amine or ammonium trying to do stuff, nitrogen gets a bit carried away and just over adds as many times as it can until it runs out of room. Okay, so a lot of this chapter is actually about how do we get it to tone it down just a little bit and go and attack just one single copy of whatever we want it to attack instead of just adding a whole bunch. So there's actually a bunch of ways to do this, some of which we've seen before. Okay. Okay, so how to make nitrogen add once only. So first option is something we saw, or related to something we saw in chapter 19 with aldehydes and ketones. So it's not animation, it's amination. We're making an amine, so reductive amination. So we're actually going to form an imine, like we did in chapter 19. And then we're going to reduce that really quickly with something pretty similar to sodium borohydride. Okay. So for example, if we have this primary amine and whatever aldehyde or ketone, if we combine these together with a little bit of acid catalyst, we're going to very temporarily get this imine. But if we do this in the presence of a reducing agent, and I'll talk a little bit about this one in a second, if we immediately reduce that down, what we're going to do, think of this as being sort of like a carbonyl, like a CO double bond. When we used a reducing agent before, we added a hydrogen to the carbon and to what was at the time an oxygen. And so we're sort of reducing this down to a single bond by adding a couple H's in there. We can do the same thing on nitrogen and reduce it down to a single bond as well. All right, so the nitrogen is only going to do this once because it's only going to form the imine once. And so we're pretty much adding this entire new chunk as a new R group that corresponds to what we used to have as the entire molecule except for the carbonyl before. Okay. Interestingly, you can actually do this even if it wouldn't really make the full imine. So even if we have a secondary amine, H plus, if you remember, or if you want to review the mechanism for this, if we have two R groups on there, a secondary amine, it's going to go through an intermediate that looks kind of like an amine, but it's the positive charge version, so iminium. And then if one of these was an H, we'd pull that right off, get to the amine, and we'd be done. But in this case, what functional group are we going to make instead? Yep, yeah, we're going to make the enamine because we can't deprotonate up here. We're going to have to pull one H off of here. But it turns out if the reducing agent is around the whole time, it doesn't even wait for that to happen. It's just going to let it get to the iminium ion, sit there for a little while while it's waiting for deprotonation, and then reduce from there. So you can still do this even if the nitrogen already has two R groups on it. So we're sticking on a third R group in this case. Again, something that corresponds to whatever this carbonyl part of the molecule was originally. Okay, so in terms of reducing agents, we're going to have to be careful about this. If we just throw the reducing agent in at the start and it's something like sodium borohydride or lithium aluminum hydride, we're going to mess this thing up before we even get going. So what people came up with was an even weaker reducing agent than sodium borohydride. So weaker than sodium borohydride. They basically took sodium borohydride and replaced several of the H's with something that reduces the negative charge on boron. So sodium cyanoborohydride. So Na plus, and then boron still has three H's, but also a cyano group on there. There's a couple other options that work about equally well, but this one's by far the most common. Okay, and if you use this reagent specifically, the guy who came up with this was called Borch So this is Borch reduction. Okay, so overall you might write this as so say we're looking at this where the carbonyl is kind of the main molecule that we care about. If we want to convert this to having an amine there instead, we could write, maybe we're trying to stick dimethylamine on there. So maybe let's use dimethylamine, sodium cyanoborohydride, HCl, and MeOH. And we're going to end up getting just a single bond to the nitrogen plus whatever it was carrying along in the first place. So those two methyl groups for the time being. Okay, so this is a nice controllable way of adding just a single R group onto the nitrogen at a time. It's not going to add twice, and you can kind of come into it from a starting material that we know a whole lot of ways to access and do things with. Okay, so I guess out of all the methods we're going to cover, this is probably the most useful and controllable. If you know one method out of this list, this is probably the one to know. All right, so I think I got 3 minutes. I can get through the second one on this list here real quick because this is a lot shorter. So acylation. This is actually what we used in the synthesis example in chapter 21, so we've already kind of seen it. So we're going to do basically form an amide. Then we're going to reduce it with LAH. So we could use acyl chloride, use NH3, make an amide, and then if we reduce it with LAH, we're going to stick on, basically replace the carbonyl with a CH2 group. So ultimately what we've accomplished from the nitrogen's perspective is we've stuck on pretty much any R group of our choice so long as it's got a CH2 at the point of attachment to the nitrogen. Okay, so this is not as versatile as Borch reduction because we're limited in exactly what kind of R group we can stick on there. Okay, but it does let us control how many R groups we add to the nitrogen at a time. Okay, questions about that one? Okay, cool. That's a good place to stop. I'll cover the next one next time.
I was wondering if I could come around 1 today to office if you're in there.
So I'm actually going to be out from about 1 to 2 or 2:30. I should be there before or after that though. So.
Or are you going to be there before 1?
Yeah, so like starting right at 12 I should be free. So, okay, cool. See you then. All right, thanks.
Right.
pick up my exam at some point?
So I actually gave them back out to the TAs already, so yeah, you have to get in touch with them. Sorry, yeah. Hey, what's up?
So this is a regrade.
Okay, cool.
And, okay, so just about that Sunday review session, I don't know how many people are in biochem, but if you do it too, then like anyone that has biochem final will be able to make it.
Okay.
So just to let you know that, but
Okay,
whatever
okay.
works.
Okay.
Can't accommodate everyone because it's impossible.
Yeah, but I prefer to get as many people as I can if people want to go.
Yeah, of course.
Yeah.
Also, just a quick question on this: why don't we add the fourth on these, but we do on the with the R groups up there?
So I think you can, but I'm not 100%
I just
sure.
curious, like, what
Yeah.
the energy like difference between like the positively charged and the or like that between those two, what would that look like?
It might just be that the methyl iodide is more electrophilic than the other two and
Okay.
easier to attack, but
Yeah.
it might also be like, I want to say maybe pKa related because you're getting like a minus charged on a more electronegative atom here, but yeah, I don't know for sure. So,
Cool.
right,
Thank you so
thanks.
much.
Yeah, no worries. Thanks. Hi.
The sodium cyanide hybrid. What exactly about the sodium and the cyanide makes it weaker?
So I think it's because, whoops, there's a, yeah. Okay, I'm gonna grab a chalk here.